Hey y'all, in this second video, I guess it's the third video, but our objective here is to study a little bit about what are called special right triangles. They're special because we're using the Pythagorean theorem to develop one particular relationship among the side lengths of this triangle, and it's fundamentally related to the angles. So let's just go for it. In each of the following examples, the triangles below exhibit special relationships between their sides. Use the Pythagorean theorem to determine the missing side lengths and form a conjecture about the pattern exhibited. That's really what that bottom part is. In this first example, if we use the Pythagorean theorem, we know that x squared plus x squared is equal to 4 times the square root of 2 squared, meaning that 2x squared is equal to 16 times 2, or that 2x squared is equal to 32, meaning that x squared is equal to 16, or that x must be equal to plus or minus 4, but since this is a triangle side length problem, the appropriate side would be 4, each of those representing 4. It just seems to me in this first example, um, these two leg lengths are the same, and that there may happen to be a relationship between this number 4 in each of the leg length and the hypotenuse having a factor of 4 outside the radical. But let's see if we can spot that pattern. And this is a similar example, I guess, but not the exact same. We're working backwards. In this case, we're given the leg lengths, and we're told to find the hypotenuse. 7 squared plus 7 squared is equal to c squared. That's 49 plus 49, which is equal to 98, is equal to c squared, or that c is the square root of 98, where 98 happens to be 49 times 2, which means a factor of 7 comes outside the radical, and a factor of 2 stays inside the radical. 7 root 2. Again, it seems like that relationship of the legs being the same length in a right triangle will produce a hypotenuse that has a factor of 7 outside the radical. And it seems that maybe just from these first two examples that the factor of inside the radical, the radicand, happens to be the 2, the square root of 2 stuff. Um, let's see if we can verify that relationship here. Oh, looky here. In this example, we're given one leg of length 8 and a hypotenuse of length 8 root 2, and we're finding the other leg length. Well, let's see if that general relationship that we saw in the first two examples is also exhibited here. 8 squared plus z squared is equal to 8 root 2 squared, or that 64 plus z squared is equal to 64 times 2. That's 128. Well, that z squared, when I subtract 64 from both sides, is 64, meaning that z better be 8. Oh my gosh, there's that relationship again. There's the square root of 2. There's the factor of 8 outside the radical for the hypotenuse, and the two leg lengths are of the same value. So if I had to generalize the relationship in this type of triangle, um, if the two legs are of the same length, we'll call each of them x. Can we generalize some value for this hypotenuse's length? Well, let's use the Pythagorean theorem. I don't know right now, so I'll just call it c. And I want to see if I can write the value of c in terms of x. So x squared plus x squared is equal to c squared. That's adding those together. 2x squared is equal to c squared. If I take the square root of both sides, c is equal to the square root of 2x squared, which there's two factors of x under the radical, meaning that this simplifies to x times the square root of 2. And that's exactly that relationship that we happen to be looking at when we discovered those patterns above, that if the two legs had the same length in a right triangle, uh, that the hypotenuse had to be that leg length, that x, times the square root of 2. And that's exactly that relationship that we saw. This triangle has a very specific name. It's called a 45-45-90 triangle. 45, 45, 90, just because it turns out that um, this is a 90-degree angle here because it's the right triangle. And if these two legs are the same length, it just so happens that the two angles, the other angles, will be the same measure. Um, Hence the name 45-45-90 as a triangle. So the following conjecture would be not even a conjecture anymore. I guess that's an established fact. If the two legs of a right triangle have a length of x, then the hypotenuse has a length of x times the square root of 2. The second type of special right triangle has a similar relationship, but it's a little more intricate, and we'll get into it just based on whether or not we can spot the relationship. But I want to start just with finding the particular values that we're asked to value or to find. A squared plus 3 squared is equal to 6 squared, according to the Pythagorean theorem, meaning that a squared plus 9 is equal to 36, or that a squared is equal to 36 minus 9, 27. So a is equal to the square root of 27. 27 happens to be 9 times 3, so one factor of 3 comes outside the radical and another stays inside. 3 times the square root of 3. It's a little early to see what the relationship happens to be in this type of triangle, so we're going to continue on into the second example, and then we'll revisit each of the examples to see whether or not we can spot the relationship. Let's use purple. Again, we can use the Pythagorean theorem to set up how to find the value of b. 5 square root of 3 squared plus b squared is equal to 10 squared. That's 25 times 3 is 75. Plus b squared is equal to 10 squared, or 100. So b squared is equal to 25, meaning that b, when I square root both sides, is 5, that this value is 5. I can somewhat start to see a relationship emerging, but I'm going to do the third example just to be extensive, just because in that first example, it looks like we're solving for the length of the long leg. I should use the green. Stay consistent. We're solving for the length of the long leg. And in the second example, we're solving for the length of the short leg. In the third example, we're solving for the length of the hypotenuse, given two of those values. That 8 squared plus 8 square root of 3 squared is equal to c squared, or that 64 plus 64 times 3, that's a it's 192 is equal to c squared, or that c squared is equal to 192 plus 64 is 256. I think that happens to be, the square root of 256 is 16. So the hypotenuse has a length of 16. So let's step back just for a moment to see if we can spot the relationship in each of these cases. It looks as though if we start with the short leg, the shorter of the leg, that's not what I meant to do. I meant to use a highlighter. If we look at the short legs, it doesn't necessarily have a particular value other than its relationship to the other two sides. That in that first example, if the short leg was 3, then the long leg was 3 times the square root of 3. In the second example, since the short leg was 5, the long leg was 5 times the square root of 3. In the third example, since the short leg was 8, the long leg was 8 times the square root of 3. Note that I'm saying leg intentionally meaning not the hypotenuse. The other thing that emerges as a relationship is that relationship between the short leg and the hypotenuse. In that first example, it seems like the hypotenuse is twice the length of the short leg. That if the short leg was length 3, then the hypotenuse was 6. And the same thing for the other two examples. If the short leg was 5, then the hypotenuse was double that at 10. If the short leg was 8, then the hypotenuse would be 16. So on the pattern exhibited, it seems as though the relationship is if I call the short leg x, then it seemed as though x times the square root of 3 would be the long leg, and 2x would be the hypotenuse. Now, we're not certain about that, but we can use the converse Pythagorean theorem to tell us whether or not that's true. That if it's possible that this is true, that's a right triangle that exists, I have to get a true statement when I apply the converse Pythagorean theorem. Is it true that x squared plus x root 3 squared is equal to 2x squared? Let's test it. That would be x squared plus, this becomes an x squared times 3, or 3x squared. Is that equal to, forgot to put that, 4x squared? Well, yeah, 4x squared happens to equal 4x squared. So yes, these are the appropriate relationships that in this particular type of triangle, if I knew the short leg was of value x, and I could establish a relationship being that the long leg was the short leg times the square root of 3, and the hypotenuse was twice the length of the short leg, then I could use the converse Pythagorean theorem to show that that was a true example of a triangle. This triangle also has a very particular name called a 30, 60, 90 triangle. A 30, 60, 90 triangle. And turns out there is a very specific orientation that the 30 and the 60 have to go into when writing the triangle, and they have to be written in that the 30 will be opposite the short leg always, and the 60-degree angle would be opposite the long leg. So let's finish this conjecture, this statement. If a right triangle has a short leg of length x and the hypotenuse is twice its length at 2x, then the long leg of the triangle has to be x times the square root of 3. And that's the relationship of a 30, 60, 90 triangle. In each of these two types of special right triangles, we may be given just one value, and we'll need to utilize the relationships known from the special right triangles in order to develop the other values of the legs. In the next video that you see, I'll do some examples that happen to do just that.